Now that you know the basics of using the CUDA.jl package, you're probably wondering how to use it in the real world. A popular use for GPGPU in the real world is for machine learning. Training a machine learning model on a CPU can take a long time, so it would be cool if we could somehow use our GPU to speed up that process. How can we do that in Julia? And what kind of performance can we expect? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I'm your host, the Dabbling Doggo.
I dabble.
This tutorial is the final video in a 3-episode arc that covers the CUDA.jl package. So I'm assuming that you've watched the last 2 episodes, and that you have CUDA installed on your computer. As a reminder, CUDA will only work with CUDA-compatible GPUs manufactured by NVIDIA. So I'm assuming that you have access to a desktop or laptop computer with a GPU made by NVIDIA. In this tutorial, I will be using the Flux.jl package to create a machine learning model that we can use with the CUDA.jl package. But this is not a Flux.jl tutorial, nor is this a machine learning tutorial. Knowledge of Flux or machine learning may be helpful, but it's not required. In this tutorial, I will provide some high-level explanations of some machine learning concepts. But if you're interested in more in-depth coverage of machine learning, I have 2 videos covering the Flux.jl package on this channel. I also have a playlist with 13 tutorials that covers machine learning in Julia for beginners. Links to those videos and the playlist are in the description below. With that said, let's jump right into the code. In VS Code, open up a new terminal window if it's not open already. Start a new Julia session by hitting Alt-J, then Alt-O. Maximize the REPL panel. Enter the package manager by hitting the closing square bracket. Activate your tutorial directory. Add the following packages: CUDA, Flux, and ML datasets. Type in status to check the version numbers. Exit the package manager by hitting backspace. Restore the REPL panel. In the Explore panel, create a new file named flux_cpu.jl. In order to save some time, I have prepared a file named flux_cpu_template.jl that's available in my GitHub repository. A link to this template file is in the description below. Select the raw version for this file, and copy this code and paste it into your file in VS Code. This file contains a modified version of the code that I used in episode 508, where I introduced the Flux.jl package. This code will create a machine learning model that can recognize handwritten digits. But before it can do that, we need to quote-unquote train this model so it can learn how to do that on its own. In episode 508, this training was done using my CPU, and it took a couple of minutes. In this tutorial, we're going to run this modified code both on the CPU and on the GPU and measure the times so we can compare the performances. Now that we have the code in our file, let's just run through this code line by line, and I'll provide some explanations along the way. This first line just loads the necessary external packages. This line loads the necessary functions from the Flux package into our workspace. And this line is for a package from Julia's standard library. Setting a random seed is not required, but I'm using it so I can reproduce my results. This line loads the training data from the ML datasets package. The MNIST dataset is a rather large file, so if this is your first time loading it, you should see a prompt asking you if you would like to proceed. Once you select Y for yes, it may take a few minutes to load, depending on your internet speed. And this line loads the testing data from the same MNIST dataset. Note that the data that we just loaded are standard 3-dimensional Julia arrays with elements of type float32. The next 4 lines of code are part of the data preprocessing step. These 2 lines of code will flatten the 3D arrays into 2D matrices so that each sample is in a column. The next 2 lines of code will encode the label data using something called a one-hot batch, which is just a matrix of booleans. And this is our actual machine learning model. Specifically, it's an example of a multi-layer perceptron, or MLP, which is a type of artificial neural network. Note that this model is using standard Julia matrices and vectors. The next few lines are necessary to set up the arguments needed to train our model. This line defines the loss function, which measures the accuracy of our model. The objective of training our model is to minimize this loss function. Flux.jl supports several different loss functions. This line is used to track the parameters. The parameters are initialized with random values, and the values will change slightly every time we train our model. Quote-unquote training our model is really just changing the parameters slightly until we find a set of parameters that gives us the most accurate model, which is measured by minimizing the loss function. Next, we select a learning rate and the optimizer that we want to use with our model. Depending on your model, you may choose to use a different learning rate and/or a different optimizer. The Flux package supports several different optimizers. Next, we select the number of epochs. Each epoch is one training session for our model. And finally, we're ready to train our model and time how long it takes. Before training our model, I need to discuss the btime macro from the Benchmark Tools package. I didn't realize this when I recorded the last 2 tutorials, but the btime macro actually runs your code multiple times, and then prints the minimum time out of all of those runs. While that may be fine for some code that can be run multiple times, it's often not a good idea to run your code several times. For example, in the last tutorial, the btime macro ran the xb function from the kubelas library multiple times. As a result, the values in the vector y were also overwritten multiple times, which is why the results were completely off. Regarding machine learning models, it's not a good idea to run full training sessions on your model multiple times. So this is a long way of me saying that I will not be using the btime macro, and that I need to find a better way to measure performance. But until I do, I will be using the time macro from Julia Base. Depending on your CPU, this may take a few minutes to run, so I will be fast forwarding through this part. Okay, it's done training. So let's take a look at the time in the REPL. This time is the total elapsed time. But if you look closer, that elapsed time also includes the time that it took to garbage collect, or GC, the memory, and the time that it took to compile the code. Garbage collection is just computer lingo for clearing memory. I'm going to be honest, this output is a little confusing to me. I've seen the percentages for GC and compilation add up to more than 100%, so it's unclear to me how these percentages are being calculated. For the purpose of this tutorial, we're going to measure the total elapsed time, and we're going to calculate the compilation time. Using those two figures, we're going to estimate the CPU runtime. There's probably something else in the runtime that we estimate, but this estimate should be good enough for our purposes. You can just copy and paste those numbers from the REPL into your file. Okay, so these are the times to beat. Next, we're going to modify these codes slightly, so we can run it on our GPU to see if we can improve these times. Close out of your Julia session by hitting Ctrl-D. In the Explorer panel, create a new file named flux_gpu.jl. Copy and paste the code from the flux_cpu.jl file into your new file. Start a new Julia session by hitting Alt-J, then Alt-O. Enter the package manager by hitting the closing square bracket. Activate your tutorial directory. Exit the package manager by hitting backspace. In order to use your GPU with Flux, all you need to do is 1. Load the CUDA package, 2. Load your data onto your GPU, and 3. Load your model onto your GPU. And that's it. Flux will do the rest. Let's go through this code line by line to see what modifications are needed. I'm going to start by changing the comment at the top. Next, be sure to include CUDA here. There are no changes needed for the next 3 lines of code, so you can just run them. Before you load the data, you need to include some syntax to load this data onto the GPU. You can do that by using the pipe operator, followed by GPU. Notice that this data has been loaded as 3-dimensional Q arrays with elements of type float32. Seeing Q arrays tells you that your data is on the GPU and not on the CPU. Simple, right? Flux does all of the heavy lifting for you under the hood. The next 4 lines of data preprocessing are the same, so you can just run them. Notice that all of these are now using the QArray data structure. In order to load the model onto the GPU, all you need to do is use the same pipe operator followed by GPU. Notice that your model is now made up of Q arrays. There are no changes to the arguments needed to train your model, so you can just run these next few lines of code. Before you train your model and time it, add the code for the CUDA sync macro. One of the challenges that I have that you won't have is that I'm recording this tutorial with a screen recorder that's taking up GPU resources. In order for me to get the most out of my GPU, I need to stop recording here. I'm going to train my model without recording it, and then I'm going to restart the recording after my model is done training. So I'll see you in a few seconds. And I'm back. My model is done training on the GPU, so let's take a look at the time in the REPL. So the total elapsed time is less than before, but take a look at the compilation time percentage. That looks a lot higher than before. Back in your editor, copy and paste the code for the CPU times and replace CPU with GPU. And then replace the times with the GPU times from the REPL. And then run each line of code for both the CPU and the GPU. Finally, let's measure the performance between the CPU and the GPU. Okay, so if we only consider the total elapsed time, then on my hardware, my GPU is about twice as fast as my CPU. But if we look at the compilation time, then my CPU is about twice as fast as my GPU. If we remove the compilation time and use the remaining time as an estimate for the runtime, then my GPU is about 5 times faster than my CPU. For the record, my CPU is the Intel Core i9-10900K, which has 10 cores with a base speed of 3.7 GHz per core. And my GPU is the NVIDIA GeForce RTX 2080 Ti, which has 4,352 cores with a base speed of 1.35 GHz per core. Your result will be different depending on your CPU and your GPU. This is a lot to take in, so let's break here and recap what we just witnessed. Training a machine learning model on the GPU in Julia is easy thanks to the flux.jl package. In order to use the GPU, be sure to include using CUDA when loading your packages. When writing your code, be sure to move your training data and your testing data to the GPU, and move your model to the GPU. You can do this in Flux by using the pipe operator followed by GPU. You'll know that your data and your model are on the GPU when you see the cuArray data structure. When you train your model, you can expect the training to run faster on the GPU, but you should also expect it to compile slower on the GPU. But overall, you should see some modest improvement in performance when training your model on a GPU versus a CPU. Of course, your experience will vary depending on your hardware specifications. Believe it or not, this concludes our exploration of the CUDA.jl package. This also concludes the tutorials for the series. I hope that you learned something interesting, and I hope that you had some fun along the way. There is one more episode left in this series, but the next episode will be a special episode to thank viewers like you. In the next episode, I'll share an annual report for this channel, and I'll share some of the lessons that I've learned during the past year. I'll also share some of my opinions about coding in general, and I'll share some of my thoughts regarding the future of this channel. A big thank you to everyone for watching this series, and a special thank you to all of my channel members and donors who make these videos possible. Well, that does it for today. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, you can support me for free by smashing that like button, leaving a comment, sharing this video, and by subscribing to this channel. If you'd like to support me financially, you can make a one-time contribution by using the Super Thanks button. You need to be logged in to see the Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julius journey.